Okay, we're just going to take a quick walk through the solutions to the circle geometry section of the MCT review. Talking about sectors here in the first couple of questions. And what you want to recognize is a sector is just a piece of an original circle. So in this case, we're saying we have 65 degrees in our sector. So something like this, but with a course of 65 in here instead. We have to determine the arc length and the area of the sector. And so essentially what we're being asked to find is the distance around the edge of the sector and the area of the sector. Well, in both cases, really what that's going to be is just a fraction of the circumference for arc length and a fraction of the area for sector. So we have 65 of the 360 degrees available to us, and essentially then we have a fraction of the regular circumference. So this is how we find circumference, and we want 65 360ths of that. With the area, or same sort of thing, we have 65 out of 360 degrees. Pi r squared is of course the area of a circle, and so that's how we're going to find those values. So there's nothing fancy here. Basically we're just saying we have a fraction of the original, so 65 360ths of whatever it is we were looking for. Question 4 then is basically the same. Given the two sectors have the same area, determine the unknown angle. So I can figure out the area of this one over here. Now, if I have a calculator, I can punch this in, of course, and get an answer. I didn't, so I just sort of treated it as a fraction. Again, 72 360ths of the total area. Knowing the radius, this will calculate to a value for the area of that sector. This sector is going to have the exact same area, and so the two areas are equal. We don't know the number of degrees out of 360 in the second case, but of course we know all the other numbers. And so even though I line them up like this, again, you can simply punch this in, get your answer here, and then make this thing equal to that number. Okay, so if the confusion was here that that I had to, the way I simplified it and so on, that shouldn't be an issue for you. Solve this one, put the number in here, and then solve for this. Multiply by 360, of course, divide by 12 squared, divide by pi, and you'll get your answer. Okay, so it says here you can punch this into your calculator to solve it. Obviously, I didn't have a calculator, but the math shouldn't be a problem for that question. So determine the length of CE. So essentially this diagram is giving me all the information I know. Now this question, again, probably not really a circle question. There happens to be a circle here that helps me maybe establish some information. But what I see is in the diagram, I have a 15 here, I have a 12 here, and I have a right angle triangle. And I'm looking for this thing, CE. And so really the fact that there's a circle here at all is just kind of a distractor. I have a 15 centimeter hypotenuse, a 12 centimeter base. I need to find the height of my triangle, and so it's a Pythagorean theorem question. Okay, so again, nothing really circle related there other than the fact that the diagram was used to help us establish our values. Now this one's a little bit more circle. Determine the value of x. Okay, so a little hard to see it here. One of the rules that we saw in this section is that given a starting or two starting points on the edge of a circle, the central angle, so the angle that is formed by going from the one edge, or from the one spot here through the center to the other spot, the angle there will be double what the angle is on the corners. Okay, so that was kind of the basis of this question. The angle in the center here is double what the angle up here will be. The angle on this side is double what this angle ends up being. And so that's kind of sort of saying from the note, this angle here is going to be double what this angle is. Again, the angle at the center spot. The angle on the center spot on the other side is double the angle on the edge at the other side. Now this pairing here, 2x plus 2y, this forms a circle. And so it must be 360 degrees, which means that the other side, the other two angles, the two angles on the edges, that each of which are half of the originals, will add up to 180. And then of course, so that's kind of the thinking that goes into the question. And then that establishes that this plus this will end up being 180 degrees. And from there, of course, it's just a matter of solving the kind of questions we saw, I guess, in grade 9. Okay. But the key, of course, is just that rule, understanding that double, or this angle, sorry, is double what that angle is. This angle is double what that angle is. Okay, BAC. So this is again a similar question. Knowing that if we have two angles on the edges here, that the central angle, the angle that goes through O here, is going to be double. So this angle is going to be double what each of these angles is. Basically, we know that these two angles will have to be the same. And so sort of that, this was my attempt at explaining that more than actually solving it. We know that anytime there's an angle coming from the edge of a circle through the center to another edge, the angle at the center is double what that inscribed angle up here would be. So the angle that goes from the same two points and meets on the edge of the circle somewhere else. So that says that this is going to be double this one. This is also double this one over here. And so clearly these two must be the exact same. So really these are just kind of questions practicing that you saw the rules and you understood the rules. So far there's been not much work to do. Now this one looks like it might be a little bit more advanced. If O is the center of the circle, okay, so O's right here, the center of the circle, and the angle is 130. So I've written in the 130 that was given to me. Determine the measure of the angles APB, so this one over here, and BOA, which is this one right, BOA, BAO, right up here. So rules we've seen before, if that's 130 there, then just kind of these two angles together form a straight line. This one in here must be 50. So it's 180 total for the straight line, minus the 130 that's already used up on the one side is 50 here. Whether that's the first step I do or just something I do at some point, doesn't really matter. It's going to be valuable to me. And then this is once more the same rule as we've had in the last two questions. Given the two starting points A and B, the central angle, the angle at O here, is 130. That's going to be double the angle at APB. So this is twice as big as the angle that starts at those same 2 points and hits on the edge of the circle. If that's the 130, that's 65. And then going the opposite direction, we have the exact same thing with starting at these 2 points, P and B. The central angle is 50. The angle up here on the edge is going to be half of that because this one has to be twice as big, and so it's 25 up here. So again, basically just knowing that rule for 3 of the last 4 questions would have got us the answer. Sort of as soon as you have 2 points on the edge of a circle, wherever they meet on the edge of the circle is the same, and it is double where they would meet in the center of the circle. Determine the length of the radius of the given circle. Okay, so I see again right angle triangle. Now again, this was one more of the rules. If you have a radius and you have a tangent to the circle, so a line that just connects to the circle at one spot, these two will meet at a right angle. And so I have a right angle triangle. Anytime I have a right angle triangle, the Pythagorean theorem is possibly a solution, or at least something that I need to consider. And so here is my C, my hypotenuse. It's the 8 from Q to the circle plus an R. So 8 plus R, and it's squared. My other two values are this length R and this length 12. So 12 squared plus R squared. And now 8 plus R squared. 8 plus R is essentially 8 plus R times 8 plus R. And as we multiply this out, 64 plus 8R plus another 8R plus R squared. So 64 plus 16R plus R squared. I've got an R squared on both sides, so if I subtract R squared from both sides, and of course that's the whole basis of solving equations, is that I can do the same thing to two sides of the equation because they were equal. If I do the same thing to them, they remain equal. And then basically subtract the 64 over here and solve R is 5. So far I would say none of the questions have been particularly hard, but knowing those couple of rules, the central angle is double the angles on the edge of the circle, and then in this case the tangent and the radius meet at 90 degrees. And of course, using this Pythagorean theorem that you would have seen back in grade 7 probably for the first time, that's come into play a couple of times just because we have triangles, and sometimes if they're right angles, like this one, then Pythagorean theorem becomes, sort of is in play as a possibility. I see two right angle triangles here as well. In this case, though, it's a little bit simpler than that. The fact that I have RP meeting at 90 degrees means it's a tangent. The fact that I have RQ meeting at 90 degrees means it's a tangent. And if we look at what we have, I have a 4 here, I have a shared side here, I have a 4 here and a shared side here. Essentially, whatever this shared side is, it can be found by doing square 16 plus square of 4 equals the square of that value. Well, if that's the case, then it turns out this side over here has to be the same as this one, because if two of the three sides and the right angle are there, this triangle is exactly the same as this triangle. I could use the Pythagorean theorem again with these two numbers to find the missing value here, and then use the Pythagorean theorem with the missing value and the 4 to find this one. But really that's kind of redundant. If I'm using the same numbers on two triangles, the two triangles are the same. That means that this value here must be the same as this value here. And of course, then we're just solving at that point.